Now, let us start lecture number 7 of Unit 1, Quantum Mechanics. In this lecture 7, we are discussing about the Davison-Germes experiment. American physicist Davison and Germes were the first person who detected an electron waves in 1927. The Davison-Germes were studying the scattered electrons from the nickel target. They found the intensity of the pattern of the scattered electron be similar to that of the X-ray diffraction. It is essentially consists of an electron gun G, target T, and made up of a large single crystal of nickel. A detector D is movable on a semicircular scale. The ends are the electrons emitted from the electron gun are collimated into a fine beam, and they are directed towards the target to strike the target, which is rotated about the axis along the direction as shown, direction of the beam as shown in the figure. The speed of electrons can be measured by the voltage of the accelerating the electrons. The scattered beam is detected by the chamber D, and its intensity is measured in different directions. The plot of an electron beam intensity I versus an angle theta is drawn. That can be seen in the figure, and where we are finding maxima and minimas. This is an experimental setup. An electron gun G. It is a filament. Cathode is heated with a high tension, and a 54 volt of potential is applied, and a high speed electrons they are made to hit to the target N, and this N, it is made up of a nickel crystal. And on the semicircle you will have a Faraday's cylinder. It is act as a detector or a collector, and that collector it is connected to a ground through a galvanometer, which measures a very sensitive current. That is the flow of electrons which are scattered, that it can be moved freely on the graduated scale. The schematic diagram of the Davison-Germes is this, and we find the intensity at different angles theta, how it is varying. It is giving a up and down graph. The experimental result it shows that an electron beam behaves like an X-ray beam. And according to de Broglie, Bragg's law, the intensity maximum minimum can be calculated by using this relation 2d sine theta is equal to an n lambda, where, or 2d sine phi is equal to an n lambda, where phi is the diffraction angle corresponding to maxima and minima, where n is the order of maxima. 2d is the interplanar spacing or spacing between the Bragg's planes. And n here it is considered as 1 for the first order diffraction. And 2d is known for the crystal planes. Hence, lambda can be found measuring phi in the experiment. So the wavelength of the moving electron can be calculated using the value of the voltage, as we know that lambda is equal to under root of 150 by V, root of V. So this, it will be equal to 12.26 under root of V according to de Broglie concept. So here lambda is equal to 2d sine theta, where d is substituted as 0.91 into 10 power minus 19 for nickel crystal, and theta is considered as a glancing angle. It will be equal to 65 degree from the figure, and lambda value can be calculated. Lambda is equal to 1.648 angstrom unit according to Bragg's principle. But according to de Broglie concept, it is 12.26 under root of V. It is in terms of angstrom. If it is, we have operated a 54 volt, then what will be the wavelength associated with that 54 potential? It will be nearly equal to 1.67. So nearly these two wavelengths, they are matching. Hence lambda is equal to 1.67. This is supporting the de Broglie's concept. So this is about the Davison-Germes experiment. Now calculation of wavelength associated with an electrons. Suppose if we are accelerating an electron with a very high tension battery HTB, is connected to an electron gun which is supplied with a potential of 54 volts. Then the first order diffraction maxima can be obtained between the incident and reflected of an electron rays at an angle of 50 degree. The maximum current can be found between the incident and scattered or reflected when it creates an angle of 50 degree. Thus, the angle of diffraction, it is 90 minus 25, it is 65 degree. Hence, the interior interplanar spacing D of a nickel crystal, it is about 2.15 angstrom. Therefore, the wavelength of an electron beam, according to de Broglie Bragg's principle, it can be calculated, it is equal to 1.65. Then, according to de Broglie, when the potential is operated with 54 volt, its value will be equal to 1.67. Hence, the wavelength of a beam, electron beam, calculated from the de Broglie concept, de Broglie's equation is almost same. Hence, the wavelength, hence the wave nature of the matter experimentally proved. This ends the lecture 7, that is on the concept which is supporting the de Broglie hypothesis. The experiment is the Davison-Germes experiment. In the examination, they may ask you to explain the Davison-Germes experiment supports the matter waves or matter wave concept. So this ends the lecture 7, Davison-Germes experiment.